So in this section, we start taking some of the concepts from the previous sections up a dimension and looking at them in R3. And so the first idea I want to mention just briefly is that of a differential operator, which is a thingy that turns one function into another function using derivatives. So that's a horribly imprecise thing to say. And in fact, instead of thingy here, I should say function. But I just didn't want to freak people out by saying that it's a function that takes functions to functions. Which is true, but a bit of a mouthful. Anyways, forget about that, and let's look at an example. So, one example that you know of is ddx. So this is the standard differential operator. It takes f to the partial derivative of f with respect to x. Another example that we'll see a bit later is called the Laplacian. It maps f to the second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z. So these are both examples of differential operators, but they're not the ones I care about today. The ones that I'm interested in right now is actually this thing, nabla, that we've been using to describe the gradient. So this guy by itself is sometimes called del. And it is a mapping that takes f to the gradient of f. So this means that del looks like this thing, this quote-unquote vector. It's actually a vector-valued differential operator. So it's this guy. So this turns out to be very useful conceptually for working with vector fields and scalar fields in R3. So let's see. So using this notation, we have the divergence of the vector field f. So, and we can write it as del dot f. So this would be ddx, ddy, ddz dotted with the vector field, which if I write it in coordinates, we can call it p, q, and r for the component functions of f. And so then when we do this dot product, we get dpdx plus dq dy plus dr dz. So that's the divergence. So previously we were just looking in R2, so we only saw this much of it right here. For R3, just do the obvious thing and extend to the third coordinate as well. And we also have the curl of a three-dimensional vector field. So the curl of a three-dimensional vector field is del cross f. And so if we write this out, we have I, j, k across the top, and then ddx, ddy, ddz, p, q, r. And if you work out the components of this thing, you find out that they are, let's see, so we get dr dy minus dq dz and dp dz minus dr dx and dq dx minus dp dy. Okay, so that is the formula for the curl. Now notice that this guy is now a vector field. It's got three components. And as opposed to the divergence, which is still a scalar field, just like it was in R2. Okay. And then, so this portion right here is what we call the K curl. And now you can see why. It's because this is actually the k vector dotted with the three-dimensional curl of f. And so I should be completely honest and say that this is the real curl. That thing that I was talking about in the previous sections and referring to as curl, that's usually called k-curl or two-dimensional curl to distinguish it from the real big bad mamma jamma vector valued curl that we're looking at right here. So let's see. Okay, so just like we had in R2, we've also got the theorems that relate some of these ideas. So namely, it's still the case that conservative vector fields are irrotational. And so that means if I apply curl to a gradient, or in other words, if I do del cross del f, then I get 0. It's also the case that curl fields are incompressible. Now this is something that's new from in R3 because we didn't used to be able to talk about taking the divergence of a curl field back in R2. This is the one that we had before in R2. The irrotationality is new. So this one reads like the divergence of the curl of f. So that's del dot del cross f is equal to 0. And you can kind of combine these ideas here by saying that if you apply del twice to a given object, be it a scalar function or a vector field, then you get 0. And so this is commonly written as d squared equals 0. So this is some kind of funky derivative, right? Applying del is some sort of differential operation. And if you do it twice, you get 0. We'll talk more about that several sections later on. For now, just to see why this is true, this one about when you take the divergence of the curl, you get 0. Imagine that we take the divergence of this right here. This is a curl field, right? This is what the curl looks like. So if I take the divergence of this, then I would be doing ddx of the first component, and then adding that to ddy of the second component, and then adding that to ddz of the third component. And you can see this is going to cancel with this guy because of mixed partial derivatives being equal. And this is going to cancel with this guy because of mixed partial derivatives being equal. And this is going to cancel with this guy because of mixed partial derivatives being equal. So it's good old Clairaut's theorem that makes this all work out yet again.